Hey guys, welcome back to SciMath, and today we're going to be talking about reduction of order method. So let's get started. So the reduction of order method is used to find solutions to second order linear homogeneous differential equations, and specifically it's used when we're given one solution and we want to find the second linearly independent solution to the differential equation. So now let's look at the general form of a second order linear homogeneous differential equation. So this is a general form of a second order linear homogeneous differential equation. Now what makes this a second order differential equation is that we have y double prime, which is the second derivative. And what makes this homogeneous is that this whole equation is equal to 0. Now if instead of that 0 we had some function, then this would be a non-homogeneous differential equation. But because there's that 0, it's a homogeneous differential equation. And once again, a reduction of order method is used to find the second linearly independent solution given that we have the first solution provided to us. So now let's look at the formula that we use to find the second linearly independent solution. So the formula that we're given y1 and to find y2, the formula is y2 is equal to y1 times integral of 1 over y1 squared times e to the power negative integral of px dx, and then that dx down there is again for the other integral once we solve the e to the negative integral. And the p of x dx is just coming from the general form where we have p of x times y prime. That's where the p of x comes from. Whatever function is being multiplied to y prime, that's what we put in the integral for the e to the power negative integral px dx. So now let's look at an example where we have to use the reduction of order method. So this is our example problem. We have t squared times y double prime plus 2t times y prime minus 2 times y is equal to 0, where t is greater than 0. And our question states that verify that y1 is equal to t is a solution, and then the second part is use reduction of order to find the general solution. Now, before we begin any of this, we have to look at our given equation and check whether it's in the general form, that is y double prime plus p of x times y prime plus q of x times y is equal to 0. So let's do that. So I wrote out the equation again, and as we can see, this is not in the general form because y double prime is being multiplied to t squared, which is a function of t, but that's not how our general form is supposed to look like. Our general form states that y double prime should only be on its own and essentially be multiplied to 1. So this t squared, we need to remove it, otherwise it's not in the general form. So to remove t squared from there, we just multiply the whole equation by 1 over t squared, or essentially dividing by t squared to get the y double prime on its own. So let's do that. So after dividing by t squared, we get that the t squares cancel out, and then 2t divided by t squared cancels out one of the t's, so we get 2 over t, and then minus 2 divided by t squared is just that. So our general form is y double prime plus 2 over t times y prime minus 2 over t squared times y is equal to 0. So now that we had this in the general form, we can actually start working with our problem, our question, and then figuring out how to solve the different parts that they're asking us. So now that we have our general form of our given question, the next step is to identify what our p of t and our q of t is in this case. And because the functions that we're given are in terms of t, that's why it's p of t and q of t instead of p of x and qx. But if the functions were in terms of x, then we would have p of x and q of x. But because it's in terms of t, we need to identify our p of t and our q of t. So when we look at our general form, for p of t, we look at what term is being multiplied by y prime. And in this case, it's 2 over t. And for q of t, we need to look at what term is being multiplied by our y. And in this case, it's negative 2 over t squared. So let's write those down. So here we've identified our p of t and our q of t. Like we said, p of t is 2 over t and our q of t is minus 2 over t squared. Now let's start solving the question. Our first part was verifying that y1 is equal to t is a solution to this equation. So for this, we simply plug in y1 is equal to t and its two derivatives. So let's do that and see how it looks like. So we have our y1 equals to t, and our derivative y1 is equal to 1, and y1 double prime is equal to 0. So we have all our we have our solution t, we have its two derivatives. Now we just plug it into this equation right here. So let's do that. And we just have to check whether it indeed equals 0. And if it does, then we've verified that y1 is equal to t is the solution to this equation. So as you can see here, once we plugged y1 and its derivatives into the equation, we get 0, which is y double prime, plus 2 over t times 1 minus 2 over t squared times t is equal to 0. So we get 0 plus 2 over t minus 2 over t, because the t squared and t cancel out here. Let's do that. This t cancels, and one t cancels here to be left with 1t. So we get minus 2 over t is equal to 0, which indeed is true, because the 2 over t minus 2 over t just equals 0. So we've verified that y1 is equal to t is indeed a solution. So y1 is equal to t is a solution. So if we verified the first part, now let's move on to doing the second part. So now the second part was finding the general solution using the reduction of order method. So we need to find our second solution, which is y2, and it's going to be linearly independent. So we have this formula that we talked about before, which is y1 times integral of 1 over y1 squared times e to the power negative integral of p of t dt, and then that dt there is just for the second integral. So our p of t we've identified as 2 over t, and our y1 is here. Our y1 is t. We know that we've verified that it's a solution. So now we need to plug in these two different things into our formula. So let's do that and start solving. So once we plug it into our formula, we get y2 is equal to t times integral of 1 over t squared times e to the power negative integral of 2 over t dt. And now the next step is seeing what we can do with first simplifying the e to the power integral. So we have in our integral, we have 2 over t dt. So that 2 is just a constant, so that can be pulled out. So let's pull it out and then see what the next step is to solve that integral. So once we pull out that that 2, which is a constant, we get integral of 1 over t dt. Now it's a matter of looking at that integral and seeing, do we know what that integral is equal to? And matter of fact, we do. We know that the integral of 1 over t dt is equal to ln absolute value t. So knowing that piece of the integral, we can substitute ln absolute value of t in the place of the integral. So let's do that. So now we have y2 is equal to t times integral of 1 over t squared times e to the power negative 2 ln of absolute value t. So now the next step is looking at the negative 2 ln of t and what we can do with that. So there is something we can do to simplify that further, and that's called the power rule for logarithms, and I'll write it down and we'll see what it is and to simplify it further. So we want to simplify negative 2 times ln absolute value t. So like I said, we use the power rule for logarithms, which states this, that e to the power k times ln of absolute value t is just absolute value t to the power k. So in our question, if you remember, I also stated that t is greater than 0 is in the question. It was a condition in the question that t is greater than 0. This is the reason that condition was given there, that t is greater than 0, is because now that we know in our question, from our question, that t is greater than 0, this absolute value t just becomes t. So in our case, we can just substitute t to the power k and not have to worry about the absolute value in the rule. So let's do that and see what happens. So like I said, according to our condition, since t is greater than 0, we have t to the power k, and in our case, when we simplified the negative 2 ln of t, we get ln times t to the power negative 2. And once we substitute that into our formula, we can see that e to the power ln is just going to cancel out with each other because they're inverses of each other, so we can cancel this out, e and ln. So now, once we cancel that out, let's see what we get from that. So once we do that, we get y2 is equal to t times integral of 1 over t squared times 1 over t squared dt, because t to the negative 2 is just 1 over t squared. So now we just simplify this further and find the integral for it. So once we simplified, we get y2 is equal to t times integral of 1 over t to the power 4 dt, because 1 over t squared times 1 over t squared is equal to 1 over t to the power 4. Now we can just flip this and get t to the power negative 4 and do power rule on this. So we have y2 is equal to t times integral of t to the power negative 4 dt. And like I said, we're going to use the power rule for integrals, which I've written over here. So the general form of the power rule for integrals is integral of x to the power n dx is equal to x to the power n plus 1 all divided by n plus 1 plus c. And for this case, we're going to ignore the plus c and not write it explicitly because we're trying to find a solution. So we're not going to include the plus c in it, and we're just going to do normal power rule. So let's do that. So once we apply the power rule, we get y2 is equal to t times t to the power negative 3 divided by negative 3, because negative 4 plus 1 gives us negative 3. And so the further we simplify it, we get y2 is equal to t times 1 over negative 3 times t to the power 3. Because we just took that t to the power negative 3 and flipped it, so we get t cubed. So that's why we have t times 1 over negative 3t cubed. So we can simplify this further and cancel out the t's. This t will cancel with this t to give us a t squared. So let's write out our final solution for y2. So our final y2 is equal to 1 over 3t squared. But we're not quite done yet. We still have to put this into the general form, or the general solution. So let's look at what that looks like. So now we have our y1 is equal to t, which is our given solution, and we found y2, which is 1 over 3t squared. And the general solution which they want us to put it in has the form y is equal to c1 times y1 plus c2 times y2, which c1 and c2 are just arbitrary constants, and we found y1 and y2. So let's put it into the general solution. So our final answers to our question is we found y2, which is 1 over 3t squared, and our general solution is y is equal to c1 times t plus c2 times 1 over 3t squared. So this is how you do reduction of order, and I hope you learned something new today and enjoyed learning it. If you did, don't forget to like, share, and subscribe. Thanks for watching.